In this session, I want to switch the material from a piezo conductor to a prisma. And a prisma is close to a conductor in the sense that you can also send an electric current through a prisma. But in some the aspect of the prisma is also quite different from a piezo conductor. So I'm going to talk about the wave propagation in prisma in this session. And on this page, let me first introduce you what prisma is. Imagine that you have a piece of solid material. For example, you have some ice in your hand, and then you burn it, and then you can melt it into water. And this solid material can be converted into a liquid. And if you continue to increase the temperature, you could evaporize the water into some gaseous phase. And same thing, if you add energy into this liquid, you could produce some vapor in this process. Now, let's continue to add energy into the system. And the energy is so strong that you pull apart the charges in this vapor molecule, and you start to separate the electron and also the ion in space, and then you create some entity. We call this the force state of the material, and this is prisma. So imagine that you have a lot of electrons and ions in this material, and in fact this usually occur in some high energy process. So it's not a surprise that we observed such a material among galaxies or on the surface of the sun, or sometimes on Earth during this Rayleigh discharge. You also see this prisma formation. And in this prisma, electrons can move quite freely, and ion can also move, but ion is heavier, so it's relatively slow when it moves. So imagine that the electrons in this prisma can conduct electricity, but at the same time, you will also introduce oscillation of the ion in this conducting process. But the time scale for the ion to move is going to be relatively longer compared with the time inducing the motion of the electrons. So in this process, you can see that it's a piezo conductor, but the electrons are less likely to meet with ion. So this means that the collisions between electrons and ion inside prisma is going to be much less compared with a piece of solid conductor. And so the fundamental difference between prisma and conductor is that you have ohmic loss inside a piece of conductor, but you don't have a lot of ohmic loss in prisma. And in the ideal case, we assume that this electron is not going to collide with the ion. So now we don't have this Ga equal to conductivity multiplying with E, just like you see it in the ohmic material. And we have to start from the intrinsic original definition of the current, and it's given by the volume charge density multiplying with the velocity of the electron. And we can spell out this volume charge density to be equal to the electron density multiplying with the electron charge. And because in prisma, the primary charge is going to be electrons. And we keep this the velocity of the electron in this expression. So we have to deal with this expression given an electromagnetic wave inside prisma. And again, we only deal with harmonic field. So we start to prepare the expression expressed by the phasor notation. And assume that you have an electromagnetic wave, a harmonic wave propagating inside prisma. then you will be expecting that this electric field will be pulling electrons, and the electron velocity is going to oscillate at the same frequency of this wave given by this force, and this is the electric force and electron can experience inside the plasma. And from Newton's mechanics, you know this force F is equal to ma, where a is the acceleration of the charge. So you can write the acceleration as the derivative of v with respect to time. And this VE again is going to oscillate at the same frequency of the wave. So you can also write down the phasor expression of this velocity. So given this, you can convert the F equal to ma into a phasor notation. On the left-hand side, this is the electric force from the electromagnetic wave. And on the right-hand side, you replace this time derivative with j omega. So you end up having an expression for the phasor of the velocity of the charge proportional to the electric field inside the plasma. And also now you can convert the current expression into phasor notation and just use the solution for the phasor of the velocity in this term, and then you can express the current as a function of electric field. And the coefficient is a little bit complicated, but in fact, I want to draw your attention that this is related to the charged electron density and also the frequency. And once you have this expression, then you can put it into Ampere's law again, because Ampere's law is going to redefine the permittivity for the wave propagating inside this material. So you put this GA into this Ampere's law and then group everything together and pull out the electric field on the right-hand side. And then if you compare this expression with the usual expression for the Ampere's law, then you can define a plasma permittivity given by this expression. And you can see that this is just equal to this epsilon p, and we call epsilon p to be plasma permittivity. And from the very beginning of this lecture, I already told you that when we deal with a wave propagating inside material, we want to define the permittivity of the wave inside the material. Once we define the wave permittivity inside the material, then we are in the position to calculate the propagation and also attenuation of the wave inside the material. So now we define this epsilon p, the plasma permittivity. Then we put it into this wave number and replace this epsilon with the newly defined permittivity. And then we end up having this propagation constant. And it's quite interesting that you have something inside this square root, and this value could be less than 0 if this value is larger than 1. And if you have the square root of something less than 0, then you're going to create a j in front of it. In other words, the k could be just the imaginary number. If you have a k equal to imaginary number, then the wave will be attenuating inside the material. So to propagate, if you put k into this expression, to propagate this wave need to have a real value of this k. So this means that the frequency has to be large enough so that 1 minus this term is a positive number. So we came up with the conclusion that this frequency has to be larger than this value. Otherwise, the wave cannot propagate inside a plasma. And so this is going to have a unit of frequency. So let's define this value to be equal to a symbol called omega p, and call this frequency to be plasma frequency. So a short conclusion is that if you want to propagate a wave inside a prisma, the frequency of the wave has to be high enough, and the frequency has to be higher than this value. And if you already define this value to be the prisma frequency, then the conclusion is that the wave's frequency has to be higher than the prisma frequency, so that the wave can propagate inside prisma. If the frequency of your wave is less than this prisma frequency, then you will end up having an imaginary k in your expression, and you will have pure attenuation of the wave inside the prisma, just like you propagate a wave into a piece of ideal conductor. You have just pure attenuation inside. So in this session, I talk about prisma, which is some material. And in this material, you have a lot of electrons moving freely. And ion can also move, but the motion of the ion is slower. And you don't have a lot of collisions inside. So the propagation of the current does not quite follow the ohmic law. And for a wave propagating inside prisma, the frequency of the wave has to be larger than the so-called prisma frequency. And this prisma frequency is related to the density of the electrons inside prisma, and also the mass of the electrons. So you can see that in this expression, E is just equal to 1.6 multiplying with the 10 to minus 19 coulomb. And this is the m is also a universal constant. M is equal to 9.1 times 10 to minus 31 kilogram. So what is critical is this Ne, which is the electron density, determine the prisma frequency. And so this is the basic concept I want to tell you when you propagate an electromagnetic wave inside prisma. Thank you.